Hi guys, welcome back to Data Every Day. Today we have a data set of sundown and sunup data from Toronto, and it's a very simple data set. It actually just has 4 columns. You can see every value in here is Toronto, so it really has 3 columns. And what we're going to do is try to predict the month of a record based on the sunup and sundown times. Alright, so I have the notebook here. Given data about daily sunrise and sunset in Toronto, let's try to predict the month of a given record. And we'll use a logistic regression model to make our predictions. So here I'm importing some standard libraries, NumPy and Pandas, of course. And then for our preprocessing, we're just going to use the standard scalar and train test split function from sklearn. And we'll be using the logistic regression model also from sklearn to make our predictions. So I'll go ahead and import those, and let's load in the data using pandas.read CSV, and we can get the file path right over here, sunup sundown data.csv. Paste that in, check it out, and like we saw, okay, so we have a good number of rows, which means we should probably have some good results. So what it looks like it might be is it goes day by day, and it goes from 2010 to 2020. And what we want to do is try to use these 2 columns as the features and use this as the label. So let's check out the info. And you can see we have no null values and everything is stored as objects. So let's start preprocessing. So we're going to have to engineer some new features from sunup and sundown and date. Date will not be a feature exactly, but it will be our label, our target. So let's keep data here and keep processing it. So let's create our label, our target column. So data sub date dot apply a lambda function that takes in some, let's say, date, and it's going to give back date indexed from 5 to 7. Not data, date. And what that does is it's going to just take these 2 characters. So we have 0, 1, 2, 3, 4, 5, which stops right after the hyphen, and then we have 6, 7, stops after the 1. So if we run that, you can see we have just 0, 1, 0, 1, 12, 12, like that. Just these months. We don't really care much for the year or the day. So this will be, we're going to make a new column called month that will be these values. So now we have this month in the end. Alright, now let's create features from here. So currently we have hour, minute in one column, but I want to create 4 features in total. Hour as one feature, minute as another feature, and then hour as one feature, minute as another feature. One for sunup, well, 2 for sunup and 2 for sundown. So data sub sunup dot apply a lambda function that here takes in a time, and it should spit back the hour. So times from 0 to 2. We should say from the beginning to 2. And this will look like this, just 07, right? Similarly, if we were to do this with sundown, we would just get 16. So what I'll do is create, well actually before I go on, I also want to say we can get these 2 from indexing from -2 to the end of the string. And that will be just the minute. See? So right here, 51. So what I'm going to do is make 4 new columns. So one will be sunup hour. And sunup hour is going to be like this, from the beginning to index 2. So just the first 2. And then I'm going to make one that's sunup minute. And this will be -2 to the end. And I'm going to copy that and do it for sundown. no, hold on. Just gonna grab all these ups. Sum down. Alright, and now if we run that and take a look at data, we now have these 4 features generated from these 2 columns. So we can check it, 751, 751, 1651, 1651. Seems to be good. Alright, and now since we have all our features, we can drop the original city, date, sun up, and sun down columns. So data equals data.drop, and then all those, so these ones. Okay. Axis 1. And if we look at data now, you can see we have, oh, I should also note data sub city dot unique. So let me just rerun this notebook. I just want to include this so we can see that there's only one value in city. That's why we're dropping it. Okay. I'll leave that down here. So now we're ready to split and scale the data. So splitting and scaling. So why don't we actually just do some quick visualization. I'm going to import seaborn and matplotlib. Matplotlib.pyplot as plt, and import seaborn as SNS. So I want to look at this a little bit. I want to see the correlations between these variables, and I want to see the distribution of the variables. So I'll make a new figure. Let's go to fig size of, this is correlation, so 12 by 10 works well. We could also do 18 by 15 if you want a little bigger. Alright, and I'm going to use SNS.heatmap to create a heat map from the correlation matrix. So I'll create the correlation matrix up here. Let's call it core, which will be data dot core, and I'm going to pass core in here. I'm going to turn on annotations, and I will give it a few more arguments, which is just going to be the minimum correlation to show and the maximum correlation to show on the scale, and then also give it a color map. Let's make it rocket. Alright, and then plot.show. What happened here? I do not know what this is. Hold on. Attempt to set identical left equals right equals 0. I'll just look this up real quick. This is because the min-max are the same. So it's saying this is the problem. Whoops. 0 size array to reduction operation minimum, which has no identity. Well, let's look at the correlation. Oh, correlation is nothing. What? Huh. Also nothing. Huh. What is this? Data looks like this. Why can't I get the correlations? Correlation matrix empty. Empty correlation matrix. Object data type. Are these really objects? Oh, that might be the problem. Data.dtypes. Ah, yes, they're all objects. Okay, so data equals data.asType numpy.int. They can all be integers. Alright, now we should have no problem. So generate this, Here we go. Okay, let me make this a little smaller. Let's do it 12 by 10. Okay, so we can see, yeah, let me put the min max back in, because right now the min is at negative 0.75. I want the min to be at negative 1. I guess the max will always be 1.0, but just keep it for consistency. Okay, so we can see that values with very low correlation are red, values with a strong negative correlation are dark, and values with a strong positive correlation are light. And looks like we have sunup hour to sundown hour. That makes sense. That's strongly negatively correlated, or correlated in some way. Sundown hour to sundown to what? This is sundown hour to sundown hour. That doesn't make sense. Oh, right. Sorry, sundown minute to sundown hour. Also has a bit of a correlation there. But aside from that, looks like we don't have very many correlations. Just nice to get this picture to see what may be affecting. The month column we're especially interested in, which is we want to see are there any strong correlations between any of the independent variables and our dependent variable, month, which looks like no. They're not strongly correlated, but hopefully some combination of them will yield a good prediction. So I also want to get the distributions. So for column in data.columns, well, let's make a new figure first. plt.figure, fig size. No, we'll start by 10 by 10, then we'll adjust. So I'm going to plot.kde Oh wait, no, it's SNS, I believe. SNS.kde plot. This is a kernel density estimation plot, which will approximate the distributions within a continuous function. So we'll data.column, and now I want to say shade equals true. Oh, it looks a little nicer. And then, yeah, plot.show. Alright, we can see that sunup hour, let's spread this out a little. So let's do 16 by 5. Okay, you can see sunup hour looks like it has 3 values it likes to take on, which makes sense, right? These are discrete. It probably doesn't make sense to do it as a KDE plot because these are all discrete, all of them. So yeah, let's do it as a hist as well instead, not SNS, plt.hist. I need to get rid of shade as well. Oh, right. Okay. So I probably shouldn't have plotted them all in the same. Okay, that's why I like KDE plot. I'm just gonna keep it, even though this is really discrete values. We're just gonna keep it because we want to see where they lie. We can see these little spikes are where the discrete values lie, and they sort of approximate a histogram, but while allowing us to see it all on one scale, so that makes it easier to visualize. So yeah, looks like, what is this, sundown minute? The minutes are much more spread out because it takes a range from 0 to 60, as you can see. But the hours take values. Yeah, this makes sense. Sunup hour is early, sundown hour is later. And it looks like there's more variation in the sundown hour than there is in the sunup hour. And then month, of course, takes on values from 1 to 12. Alright, so why don't I actually pull this back a little. 10 by 5. We can leave it at 16, whatever. Alright, now let's split and scale the data. So I'm going to split it into a y and x. Y is going to be data sub, what is it, month. And we'll make a copy of it. And then x will be data.drop month. Axis 1. Alright, then I'm going to create a scalar, which will be a standard scalar from sklearn. And this will give each column mean 0 and variance 1. So x is going to be scalar.fitTransform x. So we're fitting the scalar to x, and then we're transforming x accordingly. Alright, and then, okay, so now we're going to split into train and test set. X train x test, y train y test equals train test split, x y train size equals 70%. And we'll include a random state as well. How about 1, 2, 2? Not stand, state. Alright, now we will train. So I'm going to use a logistic regression model, and I'm going to try it out with different regularization strengths. So logistic regression from sklearn takes in this value c, which is the inverse regularization strength. So the lower value of c, the more regularization we have, and the higher the value of c, the less regularization we have. So what I'm going to do is I'm going to create a list of c's that's we're going to try out. So how about we'll try 0.01, 0.1, 1.0, 10.0, and 100.0. And we can modify this list later. Then I'm going to create a list, an empty list called models, that I'm going to add our models to. So for I in range, length of c's, model, well, actually I can do is for c, in c's, model equals logistic regression for c equals c, right? And then we'll fit the model, and we'll append it to models. So at the end we'll have one model for each of these c values, where it's been trained with a different regularization strength each time. So after that's done, we can check models, and it should be just 5 different logistic regression models, each with a new value of c. Alright, and we'll check the results. What I'll do is create a list of model accuracies that will just be the model.score on the x test, y test. So we're testing it on the test set for every model in models. That'll just be a list of our accuracies, and then we'll go and print those accuracies one after the other. So I'll just paste this in. You can see we're indexing c's and models at the same value. And alright, so it looks like for this particular task, regularization seems to mess with the model. We have remember a low value c means high regularization, and it seems like the higher the regularization, the worse the model is performing. So let's go ahead and try to lessen the regularization on this. We'll try 1,000. Let's even try 10,000. And so we'll retrain those. Now we have 7 models, and we have to add some new lines over here. This will be 5, and this will be 6. And let's take a look. Let me pull this back, and pull this back, and jump these forward 1. Alright, and it looks like at c equals 100 we get our best performance. So this model performs best with a inverse regularization strength of 100. Alright, and that will sum up today's video. So thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. So thank you so much for watching. I'll see you guys tomorrow. Have a fantastic day.